Everyone. Welcome to the seminar. Today, I'm very happy to have Professor Lei Wu from Center of Machine Learning Research, School of Mathematical Sciences of Peking University. Today, Lei will talk about a dynamical stability perspective for understanding neural network training. Thank you, Mr. Lei.
Okay, thank you for the introduction. In this talk, I will share with you that our understanding of approaches to understanding the dynamics of training neural networks. So this is outline of my talk. So basically, I will first introduce the motivation, and then I present some very important phenomena in neural network training, and which actually inspired our understanding approaches to understand stability approaches to understanding the neural network trainings. And then we will discuss the connection between the stability and the generalization. And lastly, we will discuss the stability and the optimization. So basically, the understanding the neural network training is a very important problems in deep learning. However, this problem is very challenging because the landscape of deep neural network can be very high dimensional and non-convex degenerate, and consists of many enormous local minima and set points. So presumably, the landscape can be arbitrarily bad, as shown as in the left fig plots. However, in practice, it's often observed that the training like a local gradient-based algorithm can always find the global minimum or converges very pretty well. That means the training algorithm must have certain bias. That bias needs the algorithm to explore only a very small, tiny, well-behaved regions of landscape. So basically our motivation is how to understand this kind of inductive bias induced by the gradient-based training algorithms, particularly their connections with the generalization and optimizations. So let's get started with some important phenomena which observed for the neural network trainings. So the first one is that it's observed that even though there's our deep neural networks can interpret overfitting our data, however, in practice, the stochastic gradient descent can always find the solutions that generalize very well, even without needing any explicit regularization. Like in this plot, the blue curve corresponding to the training with certain regularizations. However, they give us very good solutions with good generalizations. If we we reduce all the regularization. Particularly in this case, is the batch normalization, and you will find that the training still performs well, and more importantly, the algorithm still pick up solutions which generalize nearly as good as the one which is selected by using certain regularizations. And actually, in this networks has lots of parameters, which is much larger than the number of samples. So in these problems, presumably there should be certain overfitting issues. That means there are many solutions on the landscape which actually generalize very badly. However, our algorithm, even without any regularizations, the inductive bias of the SGD can help the algorithms to find a solution that generalize well. Even more interesting is that in practice, we always find that the SGD can generalize better than gradient descent. For example, in this table, you will find that with SGD can find solutions generalize with accuracy 95%, above 95%. And with full batch gradient descent, we'll find solution with generalized 87% accuracy. So basically, it means full batch gradient descent already generalize well, but with stochastic gradient descent, it can generalize much better. So this is actually very surprising because the stochastic gradient descent originally is proposed to speed up the training instead of improving the generalization. So there must be certain mechanism for the noise introduced by the mini batch that work to help the algorithm to find a solution which generalizes better. The third important phenomenon is called the flattened minimum hypothesis. So it's a well-known phenomenon hypothesis in deep learning theory. That is, the flat minima actually drives better than sharp minima. So in this figure, there's a trend in the community. We are trying to understand why the stochastic gradient descent final solution drives better than GD or some other algorithms. So one conjecture is that SGD can always find solutions with flat curvature around that minima. So basically, SGD find a flat minima than gradient than GD. So in these figures, this illustration of the flatness of the SGD solution and the GD solutions. So this left zero corresponding the SGD solutions and 1 corresponding the GD solutions. Then you just do an interpolation between the two minima, and then you observe. You can take a look at the landscape along this interpolation. They'll give us a one-dimensional landscape. You will find that the SGD solutions, the landscape around the SGD solution is much flatter than that of GD solutions. Okay, this observation is actually quite consistent in the in deep learning for different models and the different architecture, different data set. So the first interesting phenomena is that is observed by our work. That is actually stability, dynamic stability can already distinguish the SGD with GD. So in the let's take a look at the left figures. So basically, we first run gradient descent, full batch gradient descent, and then when the algorithm nearly convergence means the accuracy is nearly 100%. Okay, accuracy is 100%, but still the loss is not exactly 0. And then if you switch from GD to SGD, you'll find a very striking phenomenon. That is, the SGD will not converge stably. It will just escape from that minimum found by GD, and the escaping happen in just a few iterations, and then go to a very area with large loss, small accuracy. Then we'll continue to converge, and moreover, the SGD will converge to a solution which is with a better generalization or higher test accuracies. So this means that it literally means that the GD solutions picked up by gradient descent is actually dynamically unstable for SGD. And moreover, the escaping, the instability, the escaping is nearly exponentially fast. So, okay, starting from motivated by this stability escaping phenomena, we propose to, because this means that stability can distinguish the solutions or in the bias between the SGD and the GD. So we're trying to use this stability perspective to help understand why SGD always find the flat minima, and also trying to connect why the flat minima generalize better than the sharp minima. The basically means that we're trying to use stability to explain the phenomena 3 and the phenomena 2. So let's get started with the first questions. Why SGD tend to find the flat minimum? So the basic idea is quite simple, very intuitive. Let's consider the simplest case, the gradient descent. So gradient descent is given by the theta t times what? Okay, given by these iterations. And then let's look at a one-dimensional landscape. It's given by these figures. So here, A, B, C, D are the critical points of the landscape. For the gradient descent, all of these critical points are actually the fixed point of the gradient descent dynamics. Means if you start the gradient descent at exactly these points, they will always stay still in these points. However, intuitively, you will think that even A, B are the fixed point of the gradient descent, but a random initialization gradient descent will never converge to the solutions, the critical points A and B, right? It's a very intuitive. One of the reasons is that A and B are actually unstable. Basically means even they are fixed points of the dynamics, but small perturbations will drive your dynamics away from that minimum, except that you start exactly at that minimums. So that means, so basically the gradient descent only converges to solution like minimum C and D, local minimum C and D. Okay, And moreover, if the learning rate is not 0, okay, we have a large learning rate, you will actually give understanding that gradient descent can only convert to minima D instead of C. So the minima C actually has a quite sharp landscape around the minima C. So if we, for example, if we start from this point, if we choose a large learning rate, large enough, it will just escape that value, go to the upside, the other side, but with larger loss. Then it will just goes up, continue goes up, grow up, and blow up. You never convert to the solution C if the learning rate or step size is large enough, right? On the other hand, if for the larger, because the minima D is flat, it's flat. If the learning rate is small, is even for a larger learning rate, our gradient still will convert to minima D. So that means this stability argument can actually tell us that gradient descent will only select flat minima D instead of sharp minima C. So this is just the intuition. Mathematically, to analyze this phenomenon, it's actually a systematic theory in the dynamic system, which is called qualitative analysis or stability analysis of dynamic systems. So basic idea is that.
So when eta is very small, does it mean AB are stable or AB are unstable?
Unstable.
Maybe are always unstable.
Yeah.
Even with smaller.
Because A is no matter how tiny perturbations.
But when eta is very small, then you say gradient descent becomes gradient flow, then the gradient, because the gradient is 0, so even AB are stable.
Yeah, the AB are the fixed points, but they are unstable.
Oh, okay, I see.
Means that even very, very tiny perturbations to A will give us a gradient flow escape from that fixed point. Yeah. So basically, this is actually a local behavior. In this analysis, is kind of a local analysis. So locally, we know that the gradient descent, the training dynamics, actually quite nonlinear. To analyzing a highly nonlinear system can be very challenging, no matter it's a stability or whatever, any properties. However, because this is stability is kind of a local stability, so actually we only care the dynamics nearing the fixed points, right? So nearing the fixed point, we can do some perturbation analysis, linearizing your nonlinear systems. For example, basically this kind of stability analysis can be done by linearizing our dynamics locally around the minimum of interest or fixed point of interest. So basically this is given by linearizations. So if we, okay, so here it should be approximate, okay? So if theta t is close to theta star, then gradient L and the gradient L theta star should be close to the Hessian, do the tail expansion and just ignore the high order term. We'll give the reason we can ignoring the high order term is because we only care the dynamics nearing the minimum, okay? The stability can capture by this local analysis. And then locally, the dynamics is actually it's linear.
Sorry, so the reason we can ignore the high order term, because we are around the local minimum.
Yes.
It's because when the gradient is small.
Yes, and the theta t is close to theta star.
Okay.
Because the theta t is close to theta star, the high order term always will be dominated by the linear term, right?
Okay. Okay, I see.
Yeah. So it's a linear system. Then if we want the linear dynamics to be stable, a necessary condition will becomes this multiplicative constant should be smaller than 1. If it is bigger than 1, then the theta t minus theta star will grow exponentially, right? So to this condition, this quantity is smaller than 1 means that the learning rate should be smaller than 2 over the curvature of at theta star. Or in other words, given a learning rate eta, it can only select converted solutions where the largest eigenvalue of Hessian to be smaller than is unbounded by 2 over the learning rate.
So you only pick the points where the Hessian, the maximum eigenvalue of the Hessian is smaller than 2 over.
Yes, exactly.
So for any other points that's greater than this, it will continue to sort of escape from that.
Yes, yes.
Okay.
It will never convert to that regions. Even they occasionally convert to that region will just escape. Okay. So basically, this very simple stability arguments will give us that give us understanding. Stability actually controls the spectrum of hash matrix of the minimum that GD can select. And moreover, if the stability condition is not satisfied, the escaping is actually exponentially fast. This explains why, I mean, in these figures, the escaping is actually quite exponentially fast. Okay, and this is experiment for practical network. So basically, we are train convolution network for fitting fashion analysis and the CPA10. And in practice, it's more surprising is that the gradient descent not only selects solutions that satisfy the stability conditions, and select solutions that on the edge of stability. That means here the stability condition, this is inequality. However, in practice, it will become equality. So basically, you can show these experiments. So basically, we are trying gradient descent with different learning rates and to compute the spectrum of Hessian, the gradient descent solutions. You'll find that for the large learning rate, like 0.1, we'll select solutions whose eigenvalues of Hessian, large eigenvalue of Hessian is nearly close to the boundary, 20. Even for if we continue decreasing the learning rate, still holds until if the learning rate is very small. It's possible that some situations, for example, the fashion analyst will select solutions which is away from the boundary.
But what's surprising is that for every data set, it seems like you always have a flat minima where it equals to 2 over e.
Yes.
So whatever either you choose,
yeah,
will always be points that
yes,
equals to that.
Yes.
So that's a little bit
surprising.
Yeah, surprising.
Yeah, it actually means that the stability can give us even prediction of the solutions before you're training your models, can predict some properties of your models. Okay. And second, let us consider, for example, previously we are only considered the gradient descent. Then we move on to the similar analysis for stochastic gradient descent. So basic idea is the same. So first you do the linearization around the minimum of interest, and then you will give you have a SGD linear SGD dynamics. The difference from the GD is that we have the noise term, and the noise is the magnitude of the noise is 1 over the base size, and also the noise has a mean 0 and a covariance sigma theta. Sigma, by definition, sigma theta is given by the following expressions. Okay, we will come back to the structures of sigma theta. And we will use H to denote the Hessian at the global minimum of interest. So the basic lemma is following. After one step, okay, for one step, the L theta t is the loss of the current step. L theta t plus 1 is the loss of the next step. So we have for the linearized system, we have the following expressions. So compared to gradient descent, the only difference is that we have this noise term, which is proportional to square learning rate over the base size, and as well with multiply the nu theta. Nu theta is given by the trace product between the noise covariance with the local Hessian. Okay, so if we want the SG to be stable, then a natural condition is that the next step loss should be smaller, not graph, should be smaller than the current loss. So basically, if we want to derive some conditions, it's essential to understand how large the nu theta should be, and analyzing the size of nu theta needed to basically translate the problem to analyze the alignment between the noise covariance with the local Hessian, right? Because this is just the inner product, trace product between the two matrices. So it's actually quantify the alignment between the noise and the local geometry, local Hessian. Maybe just escape this derivations. I just give you a claim, okay? That is, I will claim that the sigma noise covariance is roughly So first, roughly 2 times the loss value times the G theta. G theta you can at the global minimum, G theta is exactly the Hessian. Okay, roughly think G theta as the Hessian, but it's not exactly the same. But you can, for understanding, intuitive understanding, you can think it as the Hessian. So this crude but informative approximation implies 2 messages. First one, the noise magnitude is proportional to loss value. Okay, and second, the noise, the energy. So the noise has different energy along the different directions. So it's anisotropic. It's not isotropic. Noise is not SGD noise. It's not isotropic. It's anisotropic. And moreover, the noise will concentrate on sharp directions instead of the flat directions. So this is because if you, for example, the noise energy along the given direction nu, the noise energy along this direction is given by this guy, and by this plug in this expression here will give the following. So the noise energy along the direction 这个 nu is given by 2 times the loss value times this one. This quantity is exactly the curvature between the direction nu. So basically means the noise along the flat directions will be completely zero. Along the sharp directions will large. So the noise will concentrate more on the sharp directions instead of flat directions. Okay, this is very important for understand the stability of SGD. And this is still quite different from if you take a look at the textbook for analyzing the convergence of SGD. They typically will assume that the noise is isotropic and also bounded. But however, in practice, the noise is highly anisotropic. So I just show some experiments.
So the noise here, you mean the
Mini batch noise.
The noise from the mini batch.
Yes.
Okay, so the batch is like, so the noise will concentrate on where the sharp sort of decrease of the loss. Okay, so in those directions you have more volatility. That's what you're saying.
Yeah.
And how did you get this approximation? Is it still analyzed around the local minimum?
Yeah, I just escape it. Okay, it's not a rigorous, but I can give you some intuitive. So let's consider the linear regression case. So this is our loss at the sample xi, and then this is the definition of Hessian, and we just define the G theta as the semi-positive part of the Hessian. Okay, at the global minima or around the global minima, this fitting error should be small. The Hessian should be close to the G theta, right? So temporarily you can think G theta as the Hessian, as it's not a big deal. And then you can calculate the covariance. So let's say you use EI denotes the fitting error at the I samples. Then sigma theta by definition is a gradient of loss. So gradient of loss is exactly the EI times the gradient of the model. And minus the gradient, full batch gradient times the full batch gradient transpose. If we if you acceptable, if you just ignore this term and consider only this term, and then if we assume that the fitting error and the gradient are decoupled, okay, just it's not right, but you can assume that. Then you give us these derivations. Oh, of course, basically this approximation, decoupling approximation cannot be true, right? It can give you some understanding. For example, the loss value should be proportional to the fitting errors, right? Somehow, in some sense, proportional fitting errors, and also the covariance. The curvature will also contribute to the sigma theta. So this is a very crude decoupling approximation. Will derive these equations. Okay, we won't say this is right, but I will give some theoretical argument. This is true in some sense. But we can probably it's more important to get some intuition from experiments. So basically, in this, the left hand side is for the training theta 10 with small convolution networks. You can see during the training, the total noise energy is proportional to loss value very well. And also the right hand side calculate the noise energy along the different eigen directions. So basically we compute do the eigen decomposition at the global minima, and then you calculate the noise energy along the different eigen directions. you can see along the sharp directions we has much larger noise, and along the flat directions has much smaller learning noise energies. So basically, the noise energy is proportional to the curvature of the directions. And okay, we can provide some theoretical guarantee for this intuition, but I will say it's impossible to prove this is true. The reason that, for example, this is a sigma theta is a high dimensional quantity. If you cannot expect this is the approximate becomes equality, but you can expect what we can expect that on some average, in some sense of average, it should be true. So basically, so we define the following scale factors to quantify if the approximation is true. Okay, the reason we consider nu theta, let's recall that nu theta is this quantities, which determines the stability. So for at least for the stability analysis, we only care about this quantity. So we only need to argument that the decoupling approximation makes sense in quantify use this metric nu theta. Okay, not instead of pointwise, right? Just this nu theta, this scale. So basically means that we define the new bar theta, which means this is quantity that when the approximation is true, we have a new theta, new bar theta, and then we use the ratio between the two quantity as the, how precise the approximation is true. If the approximation is true, the mu theta should be 1. And then if the approximation, okay, maybe not true, but it's good enough, the mu theta should be well behaved, it's bounding from above and below. So basically, we actually you have some theory that is the mu theta is well controlled for the whole landscape, at least for the linear networks, random feature models, and two-layer nonlinear networks. And also, you can do some experiments, validation for the practical networks. So let's look at the blue curve. Okay, just ignore the green and the orange one. The blue curve corresponding during the training, how the mu theta behave during the training. You can see that the mu theta in the training is always close to 1 for the linear networks, fully connected networks, and the convolution networks. Then the second row tests how the mu theta will change during we increasing the number of parameters of the models. And we will come back to, so in this inequality, we will claim that is the mu theta is bounded by constant, which is independent of the model size. This will be crucial in our later analysis. So we will show that even we increasing by 2 magnitude of the parameters, the mu theta is still pretty close to 1. Okay, so that the deviation is quite small. And then even for the ResNet 110 layers of ResNet, the mu theta is still close to bounding from below by constant. Okay, even in so different models have 10 million parameters, and VGG19 even have 100 million parameters, and this mu theta is still pretty close to it's not close to 1, but still well controlled during the training. Why this is actually surprising? Because so basically the mu theta quantifies the the alignment between two high dimensional vectors. If the we have 1 billion 100 million parameters, so the average the random vectors between them will be nearly orthogonal. However, here the sigma theta and h as the vectors, their dot product, normalized dot product is actually close to 0.1. It's much than the random directions, the correlations of random directions. Okay, with these assumptions, with this alignment properties, we can derive the stability conditions for SGD. That is, this quantity this instability component contributed by the SGD noise will bounding by below by the mu theta, because by definition of mu theta. So mu theta is just the mu theta times the mu bar theta. mu bar theta is given by assuming the approximation, the coupled approximation is true. That will give us the following conclusion. That is, if the alignment is bounding from below, then we'll have that SGD, if SGD is stable at this theta star, the Frobenson Hessian should be bounded above by these quantities. So this means first, this upper bound is independent of the sample size and the parameter size. It only depends on base size, alignment, and also the learning rate. And moreover, a small base size, a large learning rate will give flat minimum. So basically, this gives us understanding why large learning rate and small base size always pick up minima with a smaller sharpness or flatter.
So basically, the choice of your B represents the noise
size
of your noise size of your gradient, right? So the smaller B, the larger the variance, and hence it gives you a more flat. So okay.
And also, if you compare SGD and the GD, so the stability is quite different. In the GD, the stability will only control the sharpness, the worst case sharpness, right? The largest eigenvalue. However, SGD will control the Frobenson, which is actually in some sense the average of the sharpness. Basically, you want all the directions should be flat in some sense, instead of only the sharpest directions. That's the big difference between the SGD and the GD. And in this case, we show numerically how the bond behaves to the actual sharpness. Here, the sharpness means the Frobenson Hessian. You can show, for example, for VGG networks. So for the large networks, the upper bound is actually pretty close to the actual sharpness. And for the batch size, you can see that for small batch size regime, upper bound give us very good upper bound, very tight for the actual sharpness for Frobenson Hessian. So in this SGD case, we don't have the age of stability anymore. Okay, so they are not alike. The two curves are not exactly the same, but still they are on the same order, same magnitude. So this means this theory still, to some extent, has a prediction capability. Not, although it's not exact, precise.
But I wonder, so because your theory shows that SGD will select the flat minima, in the sense your largest eigenvalue is smaller than 1 over eta times square root of eta. What if we have multiple points of that, multiple theta that satisfy this condition? So what does it lead to?
Okay, stability can, at least my stability analysis cannot distinguish them. Okay.
So you will pick randomly one of them.
At least in our theory, yeah. Maybe that's need more analysis. Okay, so here it's actually my analysis is just a fixed point analysis, right?
Okay.
Only care our algorithm will pick up, will come to what kind of solutions. To answer your questions, we actually need to analyze the dynamics. And it also, your question depends on the initialization, and you need to track the dynamics. This is a much challenging problem. So here, the reason why I can give some prediction or predictability analysis is because I just ignore the dynamics analysis. I only care the dynamics around the minimum instead of the entire dynamics. Okay. On the other hand, if we can still show that if the stability conditions is not satisfied, then we will show that we can show that the loss will grow up exponentially fast. Basically, if the minimum, if starting from a minimum which has the sharpness is too sharp, too sharp means it's Frobenson bigger than this quantity, then the loss will grow up exponentially fast. The gamma 0 is a factor bigger than 1. Okay, grow up exponentially. Okay, explains why we here we have an exponential blow up. It's because the intuition is following. It's because the noise, our noise magnitude is proportional to the loss value, right? So if the stability condition is not satisfied, then we will escape to a region with a larger loss value. And that region have larger noise because the noise magnitude is proportional to loss value. Then this gives us a positive feedback. Then the consequently will grow up exponentially fast. So comparing, in contrast, if you assume that the noise is uniform bounded, for example, if you assume the noise is uniform bounded by some constant, then the escape is at the most linear in time t, instead of the exponential in time t. Basically, this is very important. This structure's noise magnitude is proportional to loss values. Is crucial to have this exponentially fast escaping. So here is a figure to illustrate how fast in practice is indeed exponential. So basically, you can say that in just 10 iterations, instead of 10 epochs, 10 iterations, the SCD will escape from very, very small loss to a region with constant loss in a few iterations. And the next question is why the flat minima generalize well, okay? So in the community, the popular explanation is given by this figures. So that's the black curve is an illustration of the training landscape. The dots red curve is corresponding to the testing landscape. So the testing and the training, they are not the same because there are some deviation between each other. So at least for these figures, so the flat minima, okay, the basic idea is try to say that the flat minima is actually robust to the tiny deviation. And the sharp minima is not robust to the deviation because you can see that this is sharp minima. A small deviation will go to a minima at the testing landscape with a large value, right? So this figure actually trying to argue that sharp minima is not robust to the deviation between the training and the testing landscapes. So this is very possible for the sharp minima to generalize worse, right? However, okay, this is a very intuitive, and almost all the people will use these figures to explain why flat minima generalize well. However, this explanation is quite misleading. The reason is that the deviation is not necessarily happening in this way. For example, the deviation can happen in the orthogonal to the screen. In that case, there will not distinguish between the sharp and flat. And moreover, in practice, a popular activation like ReLU activations. ReLU activation is a rescaling invariant. So basically, for any flat minima, you can rescale the network to a region with arbitrary sharpness. So that means, at least for the ReLU networks, the sharp minima can generalize very well. So this is a contradiction between this fact is contradiction with the illustration.
Yeah, just a quick question. So your argument is saying like for the sharp minima there, it could be just only sharp in one direction.
Yes.
So if your perturbation is
along the flat directions.
Orthogonal, okay. But so this paper from Ding, so they says like a sharp minima works well for ReLU is because the sharp minima for ReLU is always only in a few directions. Is that
that's a few directions? The sharpness can be arbitrarily large because that's a symmetry. So you can rescale your parameters. So basically, you have flat minima, but there are many equivalent parameters. They are implement the same networks, right? Because you can rescale the lambda. But you can look at if the lambda is go to arbitrarily large, then this minimum must correspond. This solution must correspond in some minimum with arbitrary sharpness, right? It's only because the lambda WJ can be arbitrarily large, right? So this is a contradiction with
because this is linear.
Yeah. So that means if we want to explain why flat minima generalize well, we must impose some conditions, right? And also there are some papers they are trying. We can actually construct some models. The flat minima generalize actually worse than sharp minima. It's also possible. So there's a contradiction constant examples always exist. So if we want to pursue a certain general theory to argue that flat minima always drives better, this is impossible. Or this is at least it's not a good idea. You must impose certain assumptions on the data distributions, on your model parameterizations, right? So in our work, we consider some, we're trying to develop some rigorous theories. So basically, we consider two-layer neural networks, okay? Two-layer, just a two-layer, even without bias. And also ReLU or Nick ReLU activations. And in this case, we can provide a guarantee. So as long as the sample size is mildly large, then we will show that the sharpness is proportional to the certain weighted decay of the L2 norm of the parameters. For example, for this case, the L2 norm of the Hessian is roughly the L2 norm. Oh no, that is a spectrum norm of the Hessian is roughly equal, up to constant is equal to the L2 norm of the parameters. And the Froebel's norm is equivalent to the certain weighted L2 norm. And the trace, another quantity of the sharpness is also, similar results. And it's well known that for two-layer neural networks, the L2 norm, if the model has a bounded L2 parameter, has bounded L2 norm, then the two-layer neural network must generalize well. You can provide certain theoretical guarantee. Okay. And moreover, combine this with our previous stability argument. Stability argument tells us if we choose a linear eta, eta is constant, right? For example, 0.1. We can only choose the GD only consider solution with this quantity bounded by a constant. So that's the reason. If that means given a linear eta, the gradient descent will only can only select solutions whose L2 parameters, so whose parameters, the L2 norm of the parameters is bounded by constant. That means the gradient descent with a constant linear will only consider solutions that generalize well. Even the landscape has many non-generalizable solutions. So combined two results will show that we can actually provide a theoretical guarantee.
So this is implicit regularization.
Yes.
On the norm of the parameters.
Yes.
Here only show that the norm of your weights is small, but how do you know that generalize well?
It's another problem. I didn't, but just can give this is a claim, okay?
So but this is more like proof for the implicit regularization.
Right? This here is somehow
so like you're regularizing on the parameters.
Yeah, but this regularization is given by the stability.
Yeah.
Via the sharpness. Yeah. And your questions, why the L2 norm, square L2 norm can provide effective generalization guarantee? This is another problem. It's a well-known result in the two-layer networks analysis. I won't talk about that here. And also, but here, this example has a disadvantage, that is, for both SDD and GD, they can always pick up solutions as well, because both the Froebel's norm and the largest eigenvalue will correspond in solutions with well generalization properties. And also to distinguish the generalization property of SDD and GD, we also consider another diagonal linear networks. Okay, it's another toy models. So they are linear regressions, but with the coefficient to be reparameterized by the multiplications of two parameters. For this case, the spectrum norm Hessian can only control the L infinity norm of the coefficients, effective coefficient of the linear regressions. But Froebel's law can control the L2 norm of the effective coefficients. It's well known that for the linear regressions, if you only control the infinity norm of the coefficients, it's impossible to give us, it's not enough to give us generalization guarantee. However, if you control the L2 norm or L1 norm, okay, then it will give us certain certain theoretical guarantee. But then the L2 norm corresponds to the ridge regressions. So in this case, SDD, you can argue that in this case, the stability of SDD will guarantee. It will only select solutions as well. However, the stability of GD cannot provide this kind of guarantee. In this case, so the stability can distinguish the transition between SGD and the GD. Okay. So then last part of this talk is trying to understand, the connection between the stability of optimization. Let's first recap the age of stability phenomena, which is actually, although it's found in my papers, actually emphasized, highlighted by the paper from the Cohen. So basically, in our original papers, I only mentioned that the GD well-converged solutions, which is on the age of stability for the convergent solutions. However, Cohen finds that the GD will, at the age of stability, not only nearly convergence actually happen, the age of stability happen during the large portion of the training. So basically, during the training, the sharpening will keep growing. Okay, progress sharpening phenomena. There's a progressive sharpening phenomena, and then the sharpness of the GD can travel always during the training. That will keep growing until we reach the boundary of the stability, and then we'll always stay at the edge on the boundaries, and during the on the boundaries, you can see the loss still converges. So basically, this means that the age of stability phenomenon actually occurs during the large portions of trainings. But this will be a bigger problems. That means, okay, let's just ignore this notations or whatever, these mathematical notations. Just look at these figures. This is the right-hand side, the right one. So basically, this is a counterplot of a landscape. So you can decouple your dynamics along the sharp directions and the flat directions. As I mentioned many times before, the stability is actually determined by the sharp directions. So if your learning rate is large enough, it's too large, then your training will become unstable. But this instability is caused by the dynamics along the sharp directions, right? And along the flat directions, learning rate is also along flat directions. The dynamics is always stable. So you decompose your dynamics along the sharp and flat directions. The stability of your dynamics is actually determined by the one along the sharp directions. So, and because this phenomena, the age of stability means during the training, your dynamics actually on the edge. So your dynamics is kind of brittle because the dynamics along the sharp direction is unstable. So in practice, we always want to use a large learning rate, as large as possible. However, if you somehow if you are tuning your learning rate large enough, you cannot further increase the learning rate, because if you further increase the learning rate, the dynamic along the sharp directions will become unstable. It will just grow up. However, but one idea is that you can keep the learning rate along the sharp directions unchanged, but you can only increase the learning rate along the flat directions to help your training. Okay, so this is basic idea is that we can, when tuning the learning rate, we should decouple the stable and unstable directions, and only increasing the learning rate along the flat directions. And the sharp and the stable and unstable directions can be estimated by using the sharpness. So for example, in one of my algorithms we designed, we actually estimate the diagonal of a Hessian matrix to use the Hessian, the magnitude of the Hessian to, with the coordinate with the small Hessians, small curvatures, we think this is flat directions. But this and we're only increasing the coordinate with small second order derivatives. And this will help us find okay, first, this can improve the generalization. For example, in this case, for the ImageNet, it can increase the learning, improve the generalization. Okay, it's actually not big, but still some increment, improvement. And also for the C500, they will, in this case, because with not too much data, they will give us more significant improvement for the transition. And moreover, okay, and also we are trying to use this idea to help us to improve the training of large language models, LLM. And for LLM training, this algorithm is not practical anymore because it relies on the estimate of diagonal hashing, which can be very computational and expensive. And also it's not necessarily accurate because it's only diagonal. We just ignore all the off-diagonal correlations. But for transformer, for language modeling with transformer, we find a consistent pattern for the sharpness. So basically, when we calculate the average sharpness of different blocks, like we divide the transformer into the embedding blocks, QK blocks, and the FFN blocks, and the VO block, and the normalization blocks. You'll find that for both, we have a consistent observations for the GPT architectures, the Llama architectures for different data set. We have very consistent observation of that is the embedding blocks is always the one with the smallest sharpness, and the normalization blocks always has the largest sharpness, high sharpness, and the QK sharpness of QK is tiny smaller than VO, and the VN, the FFN blocks is quite similar to the value and output blocks of the attention structures. And then a simple idea is that, okay, if we want to improve the training, you can just increase the learning. We can first, so basic idea is that, so we first tuning our algorithms and the largest with the largest learning rate. Then we keep the learning rate of the normalization blocks unchanged. And then we only change the, for example, increasing the learning rate for embedding more significantly, and also increase the learning rate of QK and VO tiny, okay, with a small multiplications. So if by applying this kind of block-wise tuning of the learning rate, we can achieve certain accelerations. For example, in this case, we are training Llama for MiniPy, for fitting MiniPy and Open Web Text data set. So you can look at this 1 billion, this Llama with 1 billion parameters. And okay, so the purple curve corresponding our models, our algorithms with block-wise learning rate. And okay, you can see that with our tuning, learning rate tuning, it can speed up the training nearly twice. And with the same steps, we actually get a gap, improve the final loss by 0.05 or 6. Okay. This increment, you may think this is a tiny improvement, but this is not the truth. Actually, in large language model training, is 0.01 is actually a significant improvement, because the training of large language model is actually quite challenging. A tiny improve of the loss, the pre-training loss, can be very important for improve the downstream performance. Presumably, we should do some shoot some experiment for the downstream performance. How if this models have a much better downstream performance than this one? Presumably, we should do that, but we haven't did that experiment yet. Okay, so in the summary, in this talk, I introduced a stability perspective of understanding the training dynamics. So the first part, we argued that the stability actually imposes capacity control of our neural networks. Okay, this explains the implicit organization of algorithms like SGD. Although we only use the algorithm like SGD as examples, but you can imagine the similar argument should also hold for the other like ADAM or adaptive algorithms. We should have the similar argument. And for the second part, we show that by decoupling the stable directions and the unstable directions, and then we can, do some learning rate increase amplification for the stable directions. They will help or improve the generalization and also the convergence optimization, even in the training of large language models. Thank you. This is my talk.
Can you go back to 2 slides? Go back 2 slides.
Which one?
So yeah, this one. So in this plot, number of steps is the number of training epoch you have.
Iterations.
Okay, iteration of updating your gradient.
Yes.
Okay, so you are in left one is 60K and the right one is 100K.
Yeah. But
Okay.
because the left one is the minipy is a smaller data set.
Yeah, that I can imagine, and it's also a smaller model.
Yes. Yeah.
Okay, I was just surprised that you use 60K iterations for the so the red one is the Adam W 60K.
6K is okay. The reason is that for the large language modeling, we typically using the cosine linear rate decay, cosine linear rate scheduler.
Yeah.
So the linear rate schedule actually depends on the the number of steps you are using. So different number of steps actually they are not directly comparable.
Okay. Right. So all the sort of the okay, and the interesting thing is that for the blockwise training, you always start with a higher loss. And
yeah, that's okay.
decrease.
That's actually very interesting questions. That deserve much investigations, more investigations. So basically, our method only outperforms the Adam W only in the later of the training.
Okay, so it means like at the starting point, you always find the worst kind of points where right for the validation loss, and then gradually you'll pick up the better one. Yeah, that's a very interesting trajectory. Like
okay, it's actually okay. It's not surprising for me. It's a kind of for example, there's a reasoning. There's a learning rate schedule very popular in. I think most of company will already use that learning rate schedule, like called Worm's WSD, warm-up stable decay learning rate scheduler. Actually, cosine learning rate scheduler is not popular or nearly abandoned in companies. Right? If you're using the WSD learning rate schedule, it will always keep a very large learning rate for many iterations until you want to get models just do some decay. So in that learning rate schedule, you will also see a similar pattern. If you compare that learning rate scheduler with the cosine decay learning rate schedule, they only outperform the cosine learning rate scheduler only in the late phase instead of the during most of the time they actually perform much worse. But this actually deserves much more investigations to see how. I think it is related to the landscape and also the linear scheduler, how it's complicated problems.